Welcome to G Fun Facts Online. Every year, colossal storms born over warm tropical waters gather strength and spin across the ocean. We call them hurricanes, and they are one of nature's most formidable forces. But we aren't helpless observers. In the face of these titans, humanity deploys a technological armada, a sophisticated network of aircraft, satellites, drones, and supercomputers, all working together in a high-stakes mission to understand, track, and predict their every move. Today, we're going deep inside this incredible story of science and courage, exploring the technological marvels that form our shield against the storm. Our story begins not with a computer, but with a dare. Before modern technology, forecasting was a guessing game based on scattered reports from ships. The Great Galveston Hurricane of 1900 hit Texas with virtually no warning, a tragic reminder of the era's limitations. Then came aviation. And on July 27, 1943, with a Category 2 hurricane churning towards Texas, U.S. Army Air Force's Lieutenant Colonel Joseph B. Duckworth, a seasoned pilot, did the unthinkable. On a bet with some British pilots, he took a single-engine AT-6 trainer aircraft and deliberately flew it straight into the swirling chaos of the storm. He and his navigator penetrated the eye wall, flew into the calm eye, and returned safely. Just to prove it wasn't a fluke, he did it again the same day, this time with the base meteorologist taking notes in the back seat. This single, audacious act proved it was possible to fly into a hurricane and gather data. It was the birth of what we now famously call hurricane hunting. This bravery paved the way for organized military weather reconnaissance, and by 1946, the 53rd Weather Reconnaissance Squadron earned the official moniker the Hurricane Hunters, a name they proudly carry to this day. The cornerstone of this effort is still a fleet of specialized aircraft that fly directly into the storm's fury. These are flying laboratories, and the workhorses are the WC-130J Super Hercules planes operated by the Air Force Reserve's Hurricane Hunters. These four-engine turboprops are built to endure. On a typical mission, lasting up to 18 hours, they fly at altitudes between 500 and 10,000 feet, repeatedly punching through the violent eye wall to reach the calm center. Their primary goal is to find the exact center of the storm and measure its intensity. The data they collect and transmit in real time to the National Hurricane Center can improve forecast accuracy by up to 30%. So how do they gather this crucial information? One of the most important tools is the dropsonde. These are cylindrical probes, about the size of a paper towel roll, packed with sensors. The crew releases them from a tube in the aircraft, and as they parachute down through the storm to the ocean surface, they constantly transmit data on pressure, temperature, humidity, and wind speed and direction. This gives forecasters a detailed vertical slice of the storm's atmosphere. Bolted to the wing of the WC-130J is another key instrument, the Stepped Frequency Microwave Radiometer, or SFMR. It looks down at the ocean and measures microwave radiation coming off the sea surface. By analyzing this, scientists can accurately calculate the wind speed right at the surface, where it matters most, and the rate of rainfall. This is critical for predicting the life-threatening storm surge. Flying alongside the Air Force are the aircraft of the National Oceanic and Atmospheric Administration, or NOAA. Their fleet includes two rugged WP-3D Orion aircraft, affectionately nicknamed Kermit and Miss Piggy. Like the WC-130s, they fly into the storm's eye wall, but they are uniquely equipped with a powerful suite of radars, including a sophisticated tail Doppler radar. These radars scan the storm horizontally and vertically, creating a detailed, three-dimensional, MRI-like map of its internal structure and wind fields. While the Orions tackle the storm's core, NOAA's high-altitude jet, a Gulfstream 4 nicknamed Gonzo, plays a different role. Gonzo flies high above and around the hurricane, at altitudes up to 45,000 feet. Its mission is to map the large-scale weather patterns, the steering currents in the upper atmosphere that dictate where the storm will go. It does this by releasing dropsondes over a wide area, feeding essential track forecasting data into the computer models. Long before a plane ever takes off, however, the storm is being watched from space. Weather satellites are our first line of defense, providing a continuous, global view that allows us to see storms form in the vastness of the ocean. The two main types of satellites, geostationary and polar orbiting, work together to provide a complete picture. Geostationary satellites, like NOAA's Goes East and Goes West, orbit at over 22,000 miles high. At that altitude, their speed matches the Earth's rotation, so they stay parked over the same spot. This gives them a constant, unblinking stare at an entire hemisphere, perfect for watching a storm's entire life cycle. The latest GOES satellites can scan the Western Hemisphere every 15 minutes and zoom in on a hurricane to capture images as often as every 30 seconds, creating a near real-time movie for forecasters. Their primary instrument, the Advanced Baseline Imager, sees in 16 different spectral bands, revealing cloud patterns and storm structure in incredible detail. They also carry a geostationary lightning mapper, which has shown that a sudden increase in lightning activity can be a sign that a storm is about to rapidly intensify. While geostationary satellites provide the constant stare, polar orbiting satellites provide the detailed flyby. Orbiting from pole to pole at a much lower altitude of about 500 miles, satellites like NOAA 20 and Suomi NPP capture data in much higher resolution. Their instruments can see through clouds, using microwaves to measure atmospheric temperature and moisture at different levels within the storm. This data is the absolute backbone of our computer forecast models, providing about 85% of the input data needed to make a 3 to 7 day forecast. One of the most ingenious uses of this satellite imagery is a method called the Dvorak technique. By analyzing cloud patterns, the shape of the storm's bands, and the temperature of the eye versus the surrounding clouds, forecasters can estimate a storm's intensity with remarkable accuracy, even when it's thousands of miles away from any aircraft. In recent years, a new class of hunter has joined the team: unmanned systems, or drones. These robotic explorers can go where it's simply too dangerous to send a crewed aircraft, providing an unprecedented look at a storm's most violent regions. A critical area for understanding a hurricane is the boundary layer, the turbulent zone in the lowest few thousand feet of the atmosphere, where the storm literally sucks its energy from the warm ocean. To sample this region, NOAA's P-3 aircraft now deploy smaller air-launched drones. The ALTIUS 600, for example, is launched from a tube in the P-3's belly. It can then be piloted remotely for hours at very low altitudes. In 2022, one of these drones flew into Hurricane Ian and measured wind speeds over 216 miles per hour, just 200-300 feet above the sea. While aerial drones probe the sky, uncrewed surface vehicles are battling the storm on the water. NOAA and the company's Saildrone deploy a fleet of wind and solar-powered USVs directly into the paths of hurricanes. These Saildrones are equipped with a special hurricane wing designed to withstand extreme winds and massive waves. They measure critical data right at the air-sea interface, helping scientists understand exactly how the ocean's heat is transferred to the storm. In 2021, a Saildrone famously transmitted the first-ever live video from inside the eyewall of a major hurricane, showing us a terrifying view of 50-foot waves and screaming winds. All of this incredible data from planes, satellites, and drones pours into the digital brains of the operation, supercomputers. These machines run enormously complex mathematical models of the atmosphere, a process called numerical weather prediction. They take a snapshot of the current state of the atmosphere using all the observational data, and then use the laws of physics to calculate how those conditions will evolve over time, stepping forward minute by minute to produce a forecast. NOAA's supercomputers can perform over 29 quadrillion calculations per second. This power allows for new higher resolution models, like the Hurricane Analysis and Forecast System, or HAFS. HAFS can zoom in on a storm's inner core with incredible detail, and it also couples the atmosphere and ocean together, simulating the crucial feedback between them. This is a major leap forward for predicting a storm's track, and, most importantly, its changes in intensity. But because the atmosphere is chaotic, forecasters never rely on just one model run. Instead, they use a technique called ensemble forecasting. They run the same model dozens of times, each time tweaking the initial conditions slightly. The result is a collection of forecasts, often shown as spaghetti plots, which display all the possible tracks. This gives forecasters a clear sense of the uncertainty. And almost always, the average of all these runs, the ensemble consensus, is more accurate than any single prediction. Since hurricanes are fueled by ocean heat, a network of sensors at and below the sea surface provides the ground truth for all this forecasting. NOAA operates a vast network of moored buoys, which are anchored to the seafloor, and smaller drifting buoys that float freely with the currents. They constantly measure things like sea surface temperature, air pressure, and wind speed. A sudden pressure drop recorded by a buoy can be the very first sign of a developing storm. To see what's happening beneath the waves, scientists deploy autonomous underwater gliders. These robotic swimmers dive down to 1,000 meters, measuring temperature and salinity to calculate the total ocean heat content, a much better measure of the fuel available to a storm than just the surface temperature. Finally, as a hurricane bears down on land, the last line of technological defense takes over: ground-based Doppler radar. The U.S. network of 160 NEXRAD radars provides an incredibly detailed look at a storm once it's within about 200 miles of the coast. The Doppler effect allows the radar to see not just where the rain is, but how fast it's moving toward or away from the radar. This reveals the storm's wind fields, its rotation, and allows meteorologists to issue specific, short-term warnings for tornadoes and flash floods. The latest upgrade, called dual polarization, sends out both horizontal and vertical radar pulses. By comparing the returns, the radar can determine the size and shape of what it's seeing. This allows for more accurate rainfall estimates and can even detect the signature of debris being lofted by a tornado, confirming that a funnel is on the ground and causing damage. From a single daredevil flight to this vast integrated global network, our ability to forecast hurricanes has grown beyond what anyone could have imagined in 1943. Each layer of this technological shield, the satellites giving the broad view, the hurricane hunters providing the truth from the core, the drones exploring the danger zones, the buoys feeling the ocean's pulse, the supercomputers predicting the future, and the ground radars standing the final watch, plays an irreplaceable role. Together, they form a system of observation and prediction that stands as a testament to our relentless drive to confront nature's power, not with fear, but with knowledge, courage, and ingenuity. And it is this pursuit that saves countless lives every single year. Thank you for listening to G Fun Facts Online.